Hello, welcome. I'm Carl Schattke, and we are going to have a presentation today and about how to stop getting stuck. And we're talking about getting stuck on PCB design changes. It's one of the nasty areas of PCB design is when you have changes and bad things tend to happen if these changes get extensive or if there's poor communication or a whole host of problems, and we're going to look at those and we're going to examine what kind of changes there are and what it takes to prepare for those changes in a winning way and how to communicate without breakdowns, and then how to break out of different design problems and break through them, and then how to create a good plan to escape out of your changes into a completed product. And we'll go over some finishing thoughts after that. So welcome, let's get started. I'd like to start by telling you a little story from my youth. When I was about 5 years old, I went to the top of this building. It's in Chicago. It's called the Prudential Building, and that's not the reason I'm telling this story. My father was an engineer, and his father was an engineer, and he worked on this building, and he was the chief electrical engineer. And this building was a new skyscraper in Chicago. It was the first one built after World War II, and it was the tallest building in Chicago at that time. And it needed lights to show how beautiful this new building was. And the chief electrical engineer was my father, but the outdoor lighting was a different engineer. And he had spec'd some lights that went on the outside of the building, and they weren't quite bright enough when they finally got the building built. And they were like all worried, and they we're like, oh, we're gonna have to tear up the grounds and put new, heavier, cables in to support that much current. And they talked to my grandfather about it. And he said, it's okay. I already put the heavier cables in. I kind of figured you might be needing them. So then this building got this beautiful, lighting to it. And, in the time that since this building was built, now it's no longer anywhere near the tallest building in Chicago. But when it was built, it was. But the thing for us to remember is that if we expect the unexpected when we're doing our original design, then we're much better prepared for, the problems that might come to us, and we're a lot less likely to get stuck. So that's the key takeaway from that. The other thing that's hard to design is when things aren't going well. So here's a picture of a ship. It's sunk. It made international news because cruise ships don't usually get stuck and beached like this, but there was a captain that did something that was not safe, and it was a danger to everybody on board. He took this large ship into an area he shouldn't have, and he didn't have plans for getting out, and there was an environmental mess, and it was bad news, and ruined a really expensive ship. And so we don't want to be doing that with our designs. We want to make good, clean, clear choices that are safe. Here's another project that didn't go well at all. This is a dam in Oroville, California. And a couple summers ago, this thing, we had some record rains, and they came down and overflowed. And they had not decided to put the right foundation on the spillway, and it started to erode, and then it eroded the area that was the earth for the dam. And this was a very, very large concern because they have a city right below this, and they had to get rid of, they had to evacuate the city for a long time. And it was a long time for this to get shored up and very expensive. When we have problems on our boards, they can be just like this. We're massive emergency and things. So we want to avoid these kind of problems. And how do you do that? Well, problems are bad. We want to avoid them. So, when I was involved in martial arts for a long time during my life, and one of the things that we would practice would be, lock positions, and we, practice on putting, our body into manipulations where we would be able to manipulate our opponent and get what would be like a lock position. If they move one way, there's pain. If they move the other way, there's pain. And really their best option at that point is just to tap out because there's no way to move. And we want to avoid getting stuck like that. So when we do our designs, we want a way out, and we don't want to design ourselves into a corner. One of my favorite things that I like to do is ride a motorcycle now, and when I took the safety training class, they taught us this process about how to avoid problems when changes are coming. They call it the SIPD process. And the idea is that you scan and look at all of the areas around you that could potentially be a problem. So you keep your eyes farther ahead and you look left to right and you keep high awareness of what's around you. And then you interpret that and you see, well, this could be a problem or that could be a problem. And then you predict what's going to happen in your mind. And then once you've made that prediction, then you decide how to, what would be the best course of action, and then you execute. So all of this happens very fast when you're riding a motorcycle, and the faster you go, the faster it has to happen. So, there's a lot of decisions that are made very quickly, but this is a plan ahead of time for making smart decisions. And the best way to get out of trouble is just don't get into it in the first place. So this is some background about why it's really important to plan when we make changes. And changes are like the weather. The more we prepare for it, the better it is for us. And so what do we need to be prepared for with circuit boards? Let's take a look at that. First little quote from Mary Shelley: "Nothing is so painful to the human mind as great and sudden change." So let's hope we don't have too much pain from that sudden change. So what are the reasons that people make changes on circuit boards? Let's take a look at that. So scope changes. There's we add or we take away functionality. The size might change. The environment might change. In this case, we got a funny looking bicycle. They said, well, keep the bicycle secure. Well, that's a scope change, but they didn't really look at the whole scope, right? We want to be able to move the bicycle later. Block of cement's not going to really work that well, but it will keep the bike in one place. Nobody's going to take it. We need to be aware of unintended consequences. In the world of change, we look at our scope, but then we also look at schedule and cost, and we're going to encounter problems with scheduling because things have to happen in the right time, the right place, the right way. We might have a sourcing problem. We might have a safety-driven challenge. We might have legal considerations why we can't sell something. There might be commercial reasons why we have some problems. So we might have real rapid schedule changes where there's either a market opportunity if we move quickly or a challenge. We might have manufacturing line down, in which case we need to respond really quickly to that kind of a situation. There might be critical path situations in the whole timeline of a project where what you're working on has to be done right away in order for the whole project to come in on time. So there's a lot of reasons for accelerating schedules, and we'll look at some ways to help do that later. And then we also might have changes because of cost or availability. So big problems right nowadays with part shortages and things like that, or there might be a massive increase in costs or massive lead times. I'm hearing lead times sometimes in a year long, in excess of a year right now for some particularly hard to get parts. So real constraint on business, and you have to redesign your way out of those, so real big reason why we see changes. And then there might be a safety driven change where something's just not safe anymore, and we found that out, and there might be legal or commercial implications with why that would be. We also might have quality reasons for change. So if we're building something and we find out we need to increase the amount of current handles, well, that's going to be a redesign. Or we need to go to higher voltage. That might be a redesign. There might be finding that there's arcing or there's calf problems with a particular circuit, and we're getting shorts there. We also might have thermal issues that we need to resolve. We also have reliability issues that could be coming up, and these could be due to vibration or solder joint failure, part cracking, being trace failure. There's a lot of different reasons why there's reliability problems on a circuit board. We might have to fix something like that, or there might be manufacturing yield problems, and company find out it's not making money from particular things, and we might want to improve the ease of assembly or improve the automation, add ICT test points. Maybe we were building in low volume and now we need to build in high volume, or we might find ourselves needing to add in circuit test points or functional tests. So quality is never an accident. It's always a result of intelligent effort. It's by quote by John Ruskin. Um, so we also have quality changes and issues that come up from our schematic. Might be logic errors, might be compiling or netlist errors. There might be a need for increasing the memory storage or decreasing it. We might find that better parts are available. We want to put those in, or there's we built it and found out that the issue was incorrect, or there might be obsoleted parts. So a number of different schematic quality issues. Not necessarily the engineer's problem, but it becomes everybody's problem once those kind of issues arrive. There's PCB design quality issues. So maybe there's a DFM, DFA, or DFT type of problem. We might find that there's signal integrity problems. Maybe the clocks aren't working right, or the diff pairs aren't, with the right, they don't have the right impedance, or there might be impedance discontinuities, or there might be problems with the way the crystals were done, or the high-speed bus, or a lot of different signal integrity problems might drive a PCB change, or power integrity problems where we have voltage drops or ground bounce or something like that, where it gives us a problem maintaining our logic levels on our circuit. Or we might have termination that's at the wrong end. We're getting reflections that are causing failures in the circuit, or op amps or power supplies that weren't weren't routed the right way, and they're noisier, and we're not passing specifications that we should be for that. Or we may have just incorrect impedance on things. A lot of different PCB quality issues can come up and cause changes, and then we get into PCB manufacturing issues. Those can also be a reason for a lot of changes. We might, need to add extra layers to support something. We might have extra steps in the process. We might want to reduce the number of layers. Drill sizes might be wrong for the parts that are on the board. We might have plating that's wrong. Maybe it's too thick and it's a more expensive board or than it needs to be, or it might be too thin and not supporting the current carrying capabilities. It might be plating, maybe we use a certain kind of plating and we find out that we have problems with that. Maybe we shows the wrong finish or something like that, or the copper balancing isn't effective. So a lot of reasons for manufacturing driving our ECO process. And then we also have assembly quality issues. So if you're trying to build something and the board's got a problem, then we have issues with assembly and it's not really working for us. And, we might have poor drawings, or documentation might be wrong, or there might be, missing ICT, or they're too close, or they're not usable, or we have a clamshell fixture and it's expensive to maintain. We might want to go to all the ICT pads on one side so they can just build a less expensive fixture, or pad sizes might be too small. There's a lot of reasons that we might want to update a board because of assembly quality issues. And then, labeling and tracking might not be done right or in the right place, or, maybe the nomenclature is not right on our boards. So a lot of changes can be driven from, quality issues. And then whenever we make changes, we need to look at the risk. So, we don't necessarily want to do things the way they were done because that's the way they always did it. No, I think that's kind of a cringeworthy statement. We want to really mitigate our risks and look at, changes to the process control. And we can, if we do make a change, we want to know if we made that change the right way. So we can cover that with, by either checking the process really carefully, like what was done, keep track of it, or we can load in the old board and the new board and use the Altium tools to compare the old to the new. And then we can also validate, those changes with a third party, maybe with, some automatic, tools for, validating the new board. And then when we do, have a change on our horizon, we want to make a quick decision so that we can still, go with a go or no go decision on doing the project. And that's calculating the possibility of success. If we try to pack 20 pounds in a 5-pound box, pretty much know it's not going to work. So we have to come up with a different solution. But a lot of changes are in the marginal kind of an area, and we may or may not succeed. And we need to make that decision quickly. So we're going to look at some tools to help with that later too. So now, the best change is one we don't have to make. Like the best fight is the one we don't have to engage in. We want to look for alternatives, right? So, we want to design for change. When we do a design, we don't want to block the ability to modify that design with our future efforts. So we want to predict growth and functionality and predict the change likelihood when we do the initial design. That's going to help us make a more logical choice in the changes and make it more possible to do that. So, when we look at changes, one of the ways that's done is the iterative process. So we see the constant, change. This would be, different organizations are going to vary in their risk profile. So there's going to be different resistance to change depending on the type of, company organization you work in, and what the total equation is as far as the reason to make a change. Some organizations you're constantly changing. It's just known that's what you're going to do. It's going to always happen. And then a certain amount of scope creep is natural, but I see often very different based on different organizations. And then scope creep gets pretty predictable if you're with an organization for a while or working with a team for a while. You kind of know how much they're going to be changing things, so you can kind of figure that into your process. And then we always, as designers, need to be really flexible as far as what kind of changes that we come in. We want to adapt to those as quickly and flexibly as possible, not present any additional obstacles, based on our beliefs, but based on like what's the best thing for for the product. Let's make those changes right away and be flexible. And then with continuous improvement, we want to go through like a plan, do, and review. So we want to plan our change, then we want to do it, and then we want to review it and make sure it was done right so that we can continue and carry on. And you can do this, with a good cooperation between the electrical and mechanical engineers and the PCB engineer to make sure that you're always doing continuous improvement, and then, go through a change and check and repeat kind of a process. And then, like we eat a meal and it's great when we have it, but the next day we're still hungry, and change is kind of like that. We do a change, and then, a few months down the road, we're still going to be hungry for a better product, and we're going to make a change. So, it's not uncommon to see boards change a lot of times based on, any of the reasons we covered earlier. Edwards Deming said that if you can't describe what you are doing as a process, you don't know what you're doing. So let's learn what this process is. Whoop. All right. So we're going to have some winning preparation to get there. All right. So I like to put change it into 4 different buckets as a designer. So first is small, easy, simple, drop in, connect, done, same day kind of stuff. These are typically real small changes, and then there's the moderate changes, a little bit more than simple, but still relatively minor, maybe 10 to 30 components. Limited active part kind of changes, small, might be 1 or 2 days to get, a redesign done on something like that. And then there's major changes. Now we're talking active parts. We might have a limited room. We're going to have to move a bunch of things out of the way. This might involve maybe a 10 to 30% change to the circuit board. It might be, in the, half a week to a week kind of time frame. And then there's like next level changes, which are complicated and involved and complex and hard and challenging way more than the other 3. And then this might be because, maybe a processor changed, or, parts in different circuits, need to relocate. We need to clear out new room for, the things that we're adding in. These would be typically your multiple day or, multiple week, multiple month kind of a change where you have pretty massive changes. So all these different kind of changes go into different buckets, and we kind of think about how we work on these based on the bucket that we find ourselves in. So, the first couple ones are relatively minor, and we can just kind of go right with whatever it is. But the major and next level changes are what we're going to be talking about for the rest of our presentation today. So, the General Sun Tzu said that if you know the enemy and you know yourself, you need not fear the result of 100 battles. If you know yourself but not the enemy, for every victory gained, you also suffer a defeat. If you know neither the enemy nor yourself, you will succumb to every battle. So be smart and know yourself when it comes to what you're trying to do in the area of PCB changes. So what are the levers? What can we control? Well, we can control placement, the area that we place it in, the rotation, the proximity of one group of placement of parts to another. We can control the order. We can control the arrangement. We can also control the priorities and, what are the critical timing delays, any noisy or sensitive areas, same layer routing, the via bound areas, the stack tolerance areas, like how much room do we physically need for, this circuit, these changes, are there magnetic components and the sensing and monitoring, power components, the sense lines. So these are the ways that we can control our circuits, and oftentimes these are leading to changes in the design, and we can control that. And then the sequence of the changes. So we get to control whether we work on the easy stuff or the hard stuff, the big stuff, the small stuff, the most likely, the least likely, the lowest risk to solve, the highest risk to solve. We can work on our schematic. We can work on it one schematic page at a time. We can choose to work from left to right, top to bottom, high voltage to low voltage, like whatever makes sense for the overall design is generally how we want to arrange the sequence. And sequencing of the changes is extremely important to having success, because if you do things out of sequence, then you're going to have to do things as you get down the process. So we can also change the rules. So sometimes if we have a change, we can change the rules in order to adopt a new technology or, change something. We can sometimes reallocate pins in relays or series circuits or pull-ups or pull-downs. Maybe they can go to a different, we can actually request changes in the schematic to make the changes easier. And oftentimes that helps us, and we need to know that that's one of the tools and levers that we can pull as a designers to request changes in that area. And then board technology is another change that we could make. If we find that we've greatly increased the density of a particular design, we could switch it to start using micro vias or pad cap vias, or we can increase the layer count, or we can increase the ground count, or the copper weight if it needs to carry more current, or we can change line widths, or there's a lot of things that we can do in order to make this change a little bit easier and not get so stuck on it. So there's usually a trade-off between the speed of the change and the cost to make the product, and more design up front generally is going to result in a lower cost product, but it might result in a change that takes longer, and there's going to be a calculus involved around that over, do I want this change super fast and get to market right away, or fix a problem right away, or do I and then come back and try and drop costs out of the product later, or do I want to lower my cost initially in the design and shoot for the lowest cost, the most efficient design from a cost perspective right away. And that's going to be a business decision based on what you have. But like Archimedes said, if you give me a lever long enough and a fulcrum on which to place it, I shall move the world. And you can move into your changes. If you know the things you can control, you can make a big difference on how well that process is going to go, and find yourself not getting stuck. If Archimedes can move the world, we can move the stuff on our circuit board. All right. Now we're going to look at communication breakdown. We're going to look, break down some of the different areas of communication that present challenges and opportunities within the communication aspect of doing changes. And this is a big part of the success of a project, is the communication that takes place between the team members. So, when we think about working on something, we want to grab the right tool. Like Maslow said, to man with a hammer, everything he encounters begins to look like a nail. And we need to be really flexible with our communication options. As designers, we, see a multitude of different ways people like to communicate. And email, I like email because you can look it up. You can look things up quickly and get things quickly. I don't like email because there's so much noise and garbage to get through just to get to what you need. So, search is real important to use email effectively. Word documents are nice to keep track of, changes in one place, kind of useful for that. And then spreadsheets are useful. You can, track them and keep track of what was done, what wasn't done. So I like spreadsheets for that reason. They're a little bit, you can also add images to spreadsheets and Word documents, but spreadsheets tend to be pretty nice from a checklist kind of a way. PowerPoint slides, pretty easy to create with just cut and paste. And then keeping like one topic per change on one slide is a pretty handy way to do things with and then there's a lot of collaborative working spaces where whenever it gets updated, then whoever's working on it is going to see that update, and you can add or subtract things to the project based on what their status is as open or closed, and very useful working tools. And then Concord Pro or Altium 365, very handy to let your coworkers know what you're working on and keep track of things. And then there's notes that you can put right on the PCB or the schematic, and you can put notes into the message. Altium has a message window where you can put things in there for people as well. So like import things like 3D shapes, like if you might, sometimes it's just physically easier to see the constraints around something by importing a 3D shape, and then you don't have to ask questions. It's just you know how big the case is, how whether things are going to fit or not. Not so much on the questions, but just having the right data at hand. And then sometimes we can get physical parts in hand, and we can look at those parts by what we can just see what it is if we can hold it. Sometimes that's better for complex parts or things like that, and then we can see like, well, if we did this or did that differently, or like this might be usable space. The image shows it's not usable space, but it probably is. So we can design denser products if we sometimes have those things in hand, and we can check relays and things like that to make sure that they work and the right polarities, things like that. And then we can also use extra mechanical layers to put things down. One of the things that's I like to do is like have a spacing layer, and I'll use like if I have a minimum distance between ICT pads, I can put a circle the same diameter as that ICT pad, and the same distance that it has to. I can put the arc the distance that the ICT pad has to be away of it, and I put 2 or 3 of those circles next to each other. It becomes immediately clear whether or not I've got the right space for all the test points that I need. So I might put those circuits on like a solder on a clearance layer, and you can use arcs and circles for soldering clearances. So if I have a selective soldering probe coming to do the soldering on through-hole parts, I need to keep my surface mount parts, like 3 millimeters away or 5 millimeters away from those through-hole pads, and not put any surface mount parts next to them. So that's a way for me to easily keep track of that visually in the design by putting that data on just a extra mechanical layer. High voltage clearances, I might put down a trace for patient isolation, so that if I know I need 8 millimeters or 10 millimeters between these two different areas on my design, I can just use a mechanical layer, put that down, and it becomes real easy to see what no traces or no components can pass past. And then I can also import shapes into 3D things if I have like complex cooling plates or something like that, where I have complex geometry mechanical situations, or I can also import that. So different ways to communicate, all good ways to make it easier to get that job done. Now, I might have said something controversial earlier. I want to train the E not to wet or go on the schematic. Well, what do I mean by that? As designers, one of the hardest things that we get when we do changes is to get a design that's not been planned for change, and then the engineer basically rips out and puts in whatever he wants and doesn't keep track of that for us, and then reuses all the reference designators. And then what happens is, if I've got a change that's extensive, 200, 300, 400 parts, and then we update that board and the designators were reused, well, then all the new parts go where the old part was, whether they belong there or not. And you have a massive hodgepodge of junk, and you have to get all the parts off the board that were new, and all the new parts have to go on to the board in a different circuit, well, now you've created a mess that can be several days of delay on a large product. And this I've seen over and over and over again. I try to train the engineers so they know not to do this. And one of the ways to not do this is to just slide those parts that you're taking off to a corner of the schematic, throw a discharge page into your schematic for compiling, get your new reference designators by keeping the old reference designators on that discard page. Now all your new reference designators have a unique reference ID, and they will not go where the old part was. They will be coming in on on the side of the board instead of right in the middle of the board where they don't belong. So big deal for people doing really large changes. If you're doing those simple and easy moderate boards, you don't need to worry about this at all. But if you're doing hard, complex kind of boards, this is a really big deal. All right, so I put this quote down here. How many times shall I forgive, said Peter. I'll tell you, not 7 times, but 77 times. That's just a little reminder for me to be nice when engineers do this. All right, so communicating around the world and remote. So a lot of problems happen when we don't understand what other people are trying to tell us, and language barriers could be a reason for that. When you have language barriers, that is going to mean that there's probably some translators. The translators might not understand the words that are written, or they might not understand engineering, and speaking engineering and language is sometimes a different language. So using text with supported images, I find really helps when there's language barrier differences. And then and then there's cultural differences. So different cultures respond to problems and situations differently. So what I like to do is employ a tell, ask, tell method. I tell them what the change is. Then I ask them to tell me what it was that they understood from me. And if they can tell me what I told them in a way that makes sense, then I have a much better idea that they really understand what I have asked to be done. Or I might be the one, following the tell, ask, tell. And I'll repeat what I heard in the way I understand it, just to make sure that, I understand what that engineer or that, manufacturing partner might be telling me. And then the other thing that I see out there is the automatic yes. So in some cultures, they might just say yes. And what yes means to them may not mean the same thing to you as what it means to the person who was saying it. So be careful of the automatic yes. And then, local customs can be quite different to what we're used to. So, different parts of the world don't think of things or relate to things the same way that we do. Our culture that we grew up in and around might not be the culture that somebody else grew up in and around, and we need to be sensitive to the differences in that and sensitive to how that might change the way that engineering would be done based on those cultural differences. And then there's conformity variances around the world. Some cultures are very conform. They have a lot of conformity to different things, and then other cultures are they're very low conformity. There's also a difference in the directness. Like how direct I am might be very different from how direct somebody from a different culture would be, or a different background. Or and this can also be based on like experience levels. So if I say something that's wrong, I should be challenged on it. I should be open to challenge. But if I say something and it's wrong and somebody's rather new, even though they know there might be a problem, they might not be willing to challenge that based on my status or their status. Like sometimes we're, a little bit in fear of making, a thing, but really we need to have the best interests of mind of everybody involved and make sure that we're not wasting money by making mistakes in our engineering. And then there's time zone constraints. So we want to present multiple options in our feedback. So if we make a request and there's a time zone involved, and we know there might be 2 or 3 different options, sometimes it's going to save us time if we can present the 2 or 3 options in our request and say, if you do this, I'd like to know this or that. And then that sometimes can save a day or, in communications, and then that's going to finish the project faster. And it helps if we can, preset our handoff times when, both parties are awake if we're dealing with time zone constraints. And then also, sometimes with 24/7 projects where you go around the clock and you're trying to get things designed as quickly as possible. So employing 2 or 3 time zones, or people working in 2 or 3 different time slots during the day is going to be another communication challenge, and we need to be aware of what goes on with that. Frank Zappa said that without deviation from the norm, progress is not possible. So we want to be open to having that deviation from the norm and looking at the unexpected in a way that can bring us progress. So now we're going to go into breaking out and breaking through, and we're going to start talking some circuit board stuff here that get into the meat of this. So what is it about changes that's going to make you successful making them? Well, we want to let the math tell us what's possible. So when we look at component density, we can do density maps, we can do density studies, how much area is there, what kind of area can be what kind of area can we expect to route based on the density. We can look at past projects and look at that density compared to what density we see on this new project or on this request. Obviously, if there's more components in the area, if there's more area for components than component area you have on your board, you have a density problem. We have the same thing with routing density. So, how many traces are going to fit through this section? Can we fit those? Is that going to actually work? We have to do the math and find out. Via density, do we have room for the vias that are going to be required, in this particular area? Am I going to be able to make a transition from my components to the inner layers to route, to other components? And I find via density is probably the limiting factor on changes for extremely high dense boards. It's like you become via bound, and that's one of the tougher problems to solve in PCB design. And then grids, if we want to make things easy for ourselves, and we can use grids in a lot of ways to make them easy. If we keep BGAs on a major whole number grid, then all of the traces are going to be exactly centered if they're also on that whole number grid. So it's easier to set up BGAs and other large parts on grid so that it's easy to tell if things are routed in the middle or not between them. And then when we work on BGAs, they're in there's a ring around that BGA, and we can put components around that BGA. And I like to use like a ring of, usually there's a lot of termination to BGAs. So like R's and C's are around it, and then there's usually some power supply support for that. So by using rings around that, that's going to create routing channels that are going to be perpendicular to the BGA, and that's going to be where we can do our north-south and east-west routing. And then we put our vias into channels between the BGA and the first row of termination, and then between the first row of termination and the second row of termination, we need to leave an area for via transitions there. And then, if it's a really big BGA, maybe a third ring or something like that. But that would be for like really, really big, complex kind of BGAs. And then the IC, like routing the power into that, usually we want to bring that from one side or two sides, and then let that power, come in from one side and try to eliminate our other circuitry from blocking the power. From effectively supplying that BGA. BGA change is probably one of the harder PCB changes that there are, because the signals from that go all directions. They're not north. They're not is easily put into rows, and the escapes are harder because there's multiple rows and multiple layers involved. We also want to be aware of room for ICT pads. So it's always important to ask up front, do we have an ICT type design, or is this going to be low volume, or we're going to just do functional tests? So there's different strategies based on that, and we can use grids for that. And then routing channels are open under rows, and so we already talked about that. So sometimes the questions are complicated and the answers are simple. That's what Dr. Seuss told us. We know how simple Dr. Seuss likes things. All right, so the best way to escape from your problem is to solve it. Robert Anthony. So routing channels, top and bottom, pin out, escape. So our most challenging problems are usually escaping from top or bottom parts with a lot of pins in a high density area, because we have to fan out and we don't have room. So now you've got vias that you have to drop in, but those take room. So And even if you have, pad cap vias, if you have a fine pitch part, you have to escape from that because the pad cap via pitch is smaller than your pad. So these are the type of problems that are generally the harder routing problems, is escaping from very high density, connectors or parts. And we find the top and bottom layers are usually where that's the most challenging. Then we also have, high voltage, boards that have very large clearances. Those can give us real hard challenges with routing escapes. And then routing density. We need to pay really close attention to how we bias the layer directions, and then also seek out, to even that density on our board, especially if we're doing more changes later, or we expect that if we keep to the X and Y locations and drop vias as needed to, maintain routing channels north and south and east and west on a board, that's going to make a big difference for our ability to complete that board. And then we also need to look at the via density in different areas. Do we need to slide things over so we have enough room to drop the vias into a particular area? These are the main tools that you'll use to solve those really, really difficult design changes. And then we need to be aware when we do drop vias in to make sure that we're not building a fence of vias where there's an opening in the ground plane, and now the return path has to take a long, windy path back instead of just directly underneath the trace. And that's going to increase the impedance, and then you're going to have fields overlapping. And when fields overlap, then that's going to create more crosstalk and potential circuit failure. So I find that vias are like the tourniquet on a dense design. Like they really, are where we get stuck and like things don't flow. So real important to look at that when we're doing our changes. Now let's look at like the basics of routing. So to me, there's like only a few different types of traces, and we use all of these in conjunction with each other, but each has its own unique advantages and disadvantages. So, the I shape, the straight connection from one place to another, is going to be your highest, most density route that there is. So a direct connection from one connection to another on one layer is always the best. It's going to have the best signal integrity. It's going to have the tightest coupling return path that there is. Next is the J shape. So this is the next highest density after the I shape, and it's basically going past a pad and then coming back. And we can use this to keep all the nets in a particular circuit on one side, and they can be nested. These are going to reverse the order of the nets. If I come from one place to another, doing a J shape is going to reverse that order. And then obviously, we can reverse the order of nets if we compare, if we pair this with an I shape type net. And then C shape type nets are the next highest density after I and J shape. And this is also going to reverse the order. Great for nesting. It makes sense on the outer edges. So if you have a layer bias on the outer edges, like a C shape kind of shape of routing is going to be very effective for those type of areas. And it's going to also give us, nice tight coupling to the return path. And it makes sense, around the edges. And then the S or Z shape, this uses up more area, but it gives us more flexibility in the routing. And then but this is also going to, keep the same shape for the design. Leonardo da Vinci said that simplicity is the ultimate sophistication. I believe that a simple routing shape is going to be the best for us as well. It always looks easiest when it's hard. The hardest things look easiest when you're done. Okay, so principles of routing. Let's seek the design flow and look for the most overall efficient use of the space. So this is going to always result in fewest number of vias, the fewest crossovers, and it's going to result in the fastest completion rates because you won't have a bunch of extra junk in the way. Fewer vias is going to be fewer blockages, especially on a through-hole design, because once you drop a via, it 100% blocks all layers on that board for that area. Whereas if you have a sequential lamination board, you can drop a via and still get routing underneath it, so it's less of a block depending on how many layers that via is going to be involved with. So higher density boards, we're almost always using blind and buried vias, that's what I'm talking about here, but in all cases, fewer vias is going to be fewer blockages on other layers. So when we route, there's so many different ways to route that board. We can, wrap things, like when I think of wrapping traces, like that's overlapping, strapping, where we go on one layer, come back, nesting, where things are building up on top of one another, folding, like if we want to change the order, we can fold those nets, sweep, and then come back on another layer. So that's going to reverse orders, twisting, basically turning over, under, around, in, out, up, down. Like we route all directions, all ways, to the best advantage. But keep that bias on your layers. That's going to be helpful. And then another tool in our belt is to use pushing and shoving. So this is basically a way to clear out particular area. That the Altium tools have pretty powerful router for this, but I find that I like to do it manually because I get a lot more control over the results, and I tend to do this manually more than automation. But I'll turn the automation on if it, for a particular area, if it makes sense. And then we can also use circular board, on boards that have arcs or circular shapes in them. We can use arcs to get the greatest routing density on those, and to route around those, we can drop arcs and space the arcs at the right distance to get that done. So whatever routing we do, we want to follow Einstein's principle of everything must be made as simple as possible, but no simpler. After we break out our boards and figure out how to route them, now, what's the way to get a great escape? Well, first we want to have a flight plan. So a few years ago, there was a crash in a river in New York, and Captain Scully brought an airline safely down in the river and saved everybody's life. And he said something about that stuck with me. He said, having a plan enabled to keep having a plan enabled us to keep our hope alive. Perhaps in a similar fashion, people who are in their own personal crisis, pink slip, foreclosure, printed circuit board design change, can be reminded to, no matter how dire the circumstances or how little time you have to deal with it, further action is always possible. There's always a way out of even the tightest spot. And, he landed a plane on the river and saved a lot of people in ice cold conditions. Kudos to Captain Sully, but I really like his idea of having a plan ahead of time for what we have to deal with. So when we think of a flight plan for our printed circuit board, this could be written or not written, but you always want to have a plan in mind, even if you're not writing it down. And you always want to know what your starting place is and what your ending place is, and then sequencing your actions so they build upon one another. That's going to create that start to end finish. And then I like to oftentimes get the easy things out of the way first, because while I'm working on the easy things, I can be thinking about how to solve the real hard problems. So sometimes I like to just do the real easy stuff first and then come and encounter the hard problems. Now, when I get complex changes, I like to locate and group the components that are unplaced by schematic pages and circuit functionality, and use that to co-locate those components and also arrange them in a way that's going to be the most dense for that particular circuit, and what I would consider to be like the ideal placement for those group of components. And then I have a block of components that I can move around, and I know how much area I need to clear for it, and I know how much room I'm going to need to drop that into a particular area. So and then once I've got those groups of components localized, and I can take them, put them on the board closest to the area that I think that they're going to go around the perimeter, and then I'll work on each of those one at a time to get that into the circuit. You always want to work on your sequence and your flight plan. You want to do first actions in a way that's going to make the later actions easier. So if you can work on something and get out of the way, now when the next thing is working on it, you don't have to avoid that or plan for room for it or over plan or under plan for it. So do things that are going to be blocked first, and then, or do things that could potentially be a block first so that you clear up the room for later. Now, Next thing you want to do is don't reuse your reference designators. Reannotation can, take place after the new parts are placed. It should never be done before. Do use rooms because that's going to help you sort your components out. Group like functions on the same page, of your schematic, and then group different types of circuits on different pages, and then keep an ECO list because that's going to help you track why things changed or why they were added. So tracking progress and sharing your updates. So hard changes can be tracked with a chart that logs over time. You want to have your parts placement completion, your connection completion, and then your total DRCs left. And if you put a chart like this together, you can see and predict how long it's going to take to finish that design up. You can see like the completion percentage, is going to get better and better as you route more of the project. Your parts placement, is going to get better and better as those parts, are on the board. And then the total number of DRCs is going to come down as that board gets more and more finalized and it's ready to produce. But that's going to be rather predictable, and you can save time communicating with management if you drop out. If you have a standard place that this gets posted, then you won't be following it. It's going to save you time in communicating with management what the status of the project is instead of having meetings all the time. So this can be a real time saver. One thing when I design a board and I'm going to get paid for it, or the company is going to have a benefit from that, is you can take the total value of that project being done divided by the remaining work to be done, and each task that needs to be done is worth that much money. So that if you have a board that's like a $25,000 design and you've got 10 traces left, they're all worth $2,500. If you get down to 2, they're worth $12,500. And that last one, you'll get it in because it's worth $25,000. Nothing's going to stop you from getting one trace in for that much. All right, so kind of a motivating thing. And Michael Dell said that anything that can be measured can be improved. I agree with him on that. And some finishing thoughts. Where there's a will, there's a way. If you believe it to be possible, you will achieve it. Begin with the end in mind. Always have an idea of what you want to do. All things are possible to a willing mind. Most important tool you have is sitting in between your ears and on your fingertips, how you deal with things. And then do the next thing. Whenever you're working on changes, like do the next thing, do the next thing, do the next thing. Don't stop until it's done. Like you have to have that next thing mentality, and then focus on one thing at a time. We want to conceptually think of all things at once, but when we do the work, we want to just be totally focused on one thing at a time. And multitasking is a myth. You don't jump all over the place. Man who chases 2 rabbits catches none. We want to have an indomitable spirit. We never want to quit, never give up. Really focus, focus, focus with complete attention to what we're trying to do. And then, always realize motivationally who you're going to help when you get finished. This is a tremendous thing to keep you going when the days get long and the nights get short. If it's more about you, if it's about more than you, then there's more of you. And I believe that, if what you're doing is going to help others and you realize it's going to help them, then you have more resources at your disposal to help them out. So thank you very much. I hope you learned a lot about doing changes on printed circuit board design and being open to change and making change and learning how to manage change. And I hope you never get stuck now because you took this course. Thank you.